live NASA television coverage of the launch of the next great Earth science satellite. The Global Precipitation Measurement mission is a constellation of international satellites. The core of that constellation is what we're hoping to watch launch today from its Japanese launch site. The launch window is scheduled to open at 1:37 p.m. That's East Coast time. It's a very different time in Japan. I'm Aries Keck here at NASA Goddard, and I'm joined by this live coverage by Dalia Kirschbaum with the GPM mission. Hi, Dalia.
Hi, how are you?
And so now we're going to be talking a lot about GPM over the next hour as we get ready to show you that live coverage. But Dalia, as being one of the GPM mission scientists, can you give us the biggest view of this mission possible?
Sure, absolutely. Well, you know, too much or too little rainfall over the Earth affects us every day, right? We have to know whether we should take an umbrella or we should leave extra time for work. You know, yesterday we had a little bit of snow here in the Maryland area, and it took us 3 times as long to get to work. So it clearly precipitation affects transportation and livelihoods and even causes casualties. But in addition to just affecting our weather every day, you know, GPM will provide important information to get precipitation around the globe and how heat is moving. So in order to understand how energy or heat is transferring from the tropics all the way to the poles, we need to have that big picture. And so GPM is going to serve as kind of the anchor, as you mentioned, to this international constellation of satellites, both domestic and our international partners. So if you think of it kind of like a lead violin in an orchestra or a lead oboe, you know, you need one satellite to help tune the orchestra to play that note. And so the GPM core satellite is really going to be that lead note to kind of unify the entire constellation and get a global picture of rain and snow every 3 hours.
And now that every 3 hours aspect of it, is that because we have a constellation of satellites or because the data rates are so fast, because the computers are faster? What leads to that 3 hours part?
Both, everything. So the GPM core satellite is actually going to orbit from about the Arctic to the Antarctic Circle, and it relies on all of these other satellites to get that global coverage. So some of the unique things about GPM is it's going to have the most advanced instruments to measure rain and snow from space, everything from light rain to heavy rain and snow, drizzles to downpours. So one of the instruments is a dual frequency precipitation radar. And so it uses kind of like a CAT scan of the body, layer by layer through the clouds. It tells us about precipitation. The other instrument is the GPM microwave imager, or GMI, and that's like an X-ray. So together, these two different measurement instruments can tell us a whole lot about what's happening at the individual precipitation scale.
And now that idea of having the lead violinist stand up there, that was a great analogy. One of the things about this international partnership is it's not just the constellation that's a partnership, right? The satellite that we're hoping to see launch today is also an international partnership, right?
Exactly. So GPM is co-led by NASA and the Japan Aerospace Exploration Agency. Now it was actually built, the satellite was built and assembled here at NASA, and one of the instruments were provided, the GMI, by Ball Aerospace. But JAXA provided the other instrument, the DPR, and is actually going to be launching in just a little bit on an H-IIA rocket. Now to hear a little bit more about the process of how this engineering and integration of instruments happened, we're actually going to have a video that was pre-recorded from the GPM project manager, Art Azerbaijan, and deputy project manager, Candace Carlisle, who currently are both in Japan and running the mission operation control here at Goddard. So let's hear a little bit more from them.
Before we launch any spacecraft, we do a very lengthy and detailed set of tests to make sure that the spacecraft is going to survive all of the environments that it's going to see during the launch and on orbit.
The test program for the observatory is pretty rigorous, and that's because once we get into space, we have only one shot at this.
The next thing we do is make sure that everything's still working after the full suite of environmental tests. So we do deployments of the solar arrays and the GMI and the high gain to make sure those still work just the same way they did before we went into environments.
The GPM Observatory is about 3,900 kilogram spacecraft fully loaded. Very large spacecraft, and the larger the satellites is, just the logistics of moving them from one location to another is much more complicated than when you're dealing with the small satellites. That's why spacecrafts or observatories like GPM Core Observatory takes longer for us to complete the manufacturing and testing and all the environmental testing that we need to at the end.
Here at Goddard, we have about 300 people working on GPM, about 100 civil servants and about 200 contractors. That's in addition to a number of people at the Japan Aerospace Exploration Agency who worked on the DPR instrument, and at Ball Aerospace who worked on the GPM microwave imager instruments.
Hi, you're watching live NASA coverage of the launch of the GPM satellite. We expect that launch window to open at 1:37 p.m. East Coast time. You caught me just looking here on my device here. We're going to be answering your social media questions as they come in. So please send them our way with GPM, #GPM or #AskNASA. We also have now, if you can see over my shoulder, live footage from Japan of the rocket on the launch pad. We're going to be giving you updates about the rocket, the satellite, the science of this mission, and all the other details that are going to be happening. Again, I just noted that the launch window is still 1:37 p.m. East Coast time, so stay tuned here. I'm Aries Keck here at NASA Goddard Space Flight Center, and also here at NASA Goddard Space Flight Center are the mission control rooms for watching this launch, not only to make sure that the rocket goes off all right, but to make sure that the satellite itself unfurls properly, achieves orbit properly, turns on properly. We have both launch operations and mission control. And in that video you just saw with Candace Carlisle, she is in one of those rooms very carefully and cautiously, I imagine, watching this footage as it comes through from Japan. There's the other big room with everyone in it. We're going to be bringing you live pictures of this throughout the entire event as it happens. And now joining me here in the Goddard TV studios is Dr. Dalia Kirschbaum, GPM mission scientist. Dalia, thanks so much for joining us.
Thank you. We're so excited for this launch.
And now when I was caught a second ago looking at Twitter, we had a question come in through Twitter using #GPM, so please use that so I know to look for it. And that question asked about another satellite, not GPM, but one called TRMM, or TRMM. How are they related?
Well, GPM is actually building off a long legacy of TRMM, the Tropical Rainfall Measuring Mission. Now, this mission was launched in 1997, and it was also co-led by NASA and JAXA. And so since then, it's been providing unprecedented data, over 16 years of data, looking at the tropics and mid-latitudes. Now, what you're seeing here is actually the launch of TRMM on an H-2 rocket from Japan, from Tanegashima Space Center. Now, since its launch on Thanksgiving Day of 1997, it has given us amazing insights into the tropics, understanding tropical convection, but also looking at hurricanes and how hurricanes intensify and move. And so TRMM has provided that amazing legacy that GPM is now building off of with advanced instruments and a broader orbit from the Arctic to the Antarctic Circle. And so we're just so excited and hope that GPM has as much success as TRMM does.
Yeah. It was really neat to see some footage of a rocket lifting off, and I caught it in the corner of my eye and was immediately like, wait, I thought it was coming later. So that was TRMM, if anyone dialed in the middle of that. That was a satellite that went up a few years ago. But it was a very similar situation. It's an international partnership mission with Japan.
That's right.
And it studies very similar things, but it really laid the groundwork for the GPM mission. We are here live at NASA Goddard, and we have scientists and engineers who are going to be joining us live here in the studio as we go along. Of course, joining me right now is Dr. Dalia Kirschbaum, with the GPM mission scientist. But in addition to scientists and engineers, we also have a number of other people here at NASA Goddard and at NASA, all the other centers, doing educational outreach and things like that. And I know Dalia has been one of the people heading up that effort.
That's right. So we have lots of different launch parties all over the U.S., even around the world. And so we just want to give a little shout out to everybody who's watching the launch right now, who's hosting a party. We really appreciate all of your involvement, are really looking forward to continuing a conversation with you in the future. And again, if you have any questions, please contact us via social media. We'd be happy to answer them.
And so now with those things, again, it's #GPM or using the #AskNASA, and we'll monitor them. If you want to be tracking this as the entire event unfurls, there's a number of Twitter accounts that are retweeting this, but the main one for the GPM mission for the last few years, and hopefully for the next few years after this, is going to be at NASA_rain. And it's the satellite's, the actual Twitter account for the satellite there. We're here live in NASA Goddard Space Flight Center. I'm hearing that we're still on track for 1:37 p.m. We'll be getting you updates as those happen throughout the entire day. And we'll also be continue to have live footage of the rocket as it sits there on the launch pad in Tanegashima Island.
That's right. And you know, as excited as we are about this launch and what GPM will provide, there's sadness in our hearts as we remember project scientist Dr. Arthur Howe. Arthur was truly the one who made GPM what it was, and his unwavering efforts to work with the international community, to work with all of our partners, made GPM a global mission with a global team. He also worked with all types of people, management, engineers, scientists, and that was really key to GPM's success, and his drive to achieve both key scientific oversight as well as applications goals was unparalleled. He was a thoughtful and he was a gracious person as well as an excellent scientist, and today of all days we sorely miss his presence here. Now, in addition to being a tremendous scientist, he actually had amazing creative vision, and so he was heavily involved in a lot of the education and outreach activities leading up to this GPM, kind of the pinnacle of what we have now. And so he helped design and think about a new film that we developed for Science on the Sphere, and it actually has 100 venues worldwide, and the film is called Waterfalls. It talks about fresh water, what happens when we have too much or too little of it, and why it matters. And so we're going to show a little excerpt from Waterfalls now to give you a sample. But if you have any interest or know of a Science on a Sphere venue near you, this video, Waterfalls, will be streaming and is available now.
Hi, you're watching live NASA television coverage of what we hope will be the launch of the GPM Measurement Mission satellite. That launch is on track for the window to open at 1:37 p.m. East Coast time. I'm Aries Keck here at NASA Goddard, and I'm joined for this live TV broadcast by Dr. Dalia Kirschbaum of the GPM Measurement Mission and by Walt Petersen now. Walt Petersen is the GPM Ground Validation Science Manager, and he's based out at Wallops, which is on the East Coast. People here on the East Coast have probably seen a few rocket launches light up their nights lately with all the launches they've been doing out of Wallops. Thanks so much for joining us, Walt.
Thank you, Aries.
All right, and so we're going to launch the satellite into orbit. We've been talking about a constellation of satellites and how important it is to be seeing things from space. You're the ground validation manager. How do you fit into all this?
Yeah, so my job basically is to coordinate the science and the measurements required to make sure that we have the best precipitation product that we can make for GPM. That includes checking the accuracy of the spaceborne products, but also improving the ground-based products as well.
So we just saw a little excerpt from a film about fresh water and waterfalls. And so really my first question is, why can't we use rain gauges on the ground?
Right, so when we say on the ground, of course, 71% of the planet is actually covered by ocean, which presents obvious problems for using rain gauges. The other part of it is if you take all the rain gauges that we have on the planet on land surfaces and you put them all together, you get about 2 basketball courts worth of area covered, okay? So, and they're really non-uniformly distributed around the globe as well. So our best rain gauge products really can't do the job for us. Radars make it a little better, but they have their own problems and not all countries have radars. So we really need that to get that globally uniform measurement from space. Well, we've got to have the vantage point of space, and we really need missions, satellite missions like GPM to do that.
Absolutely, I couldn't agree with you more. But let's talk, let's talk a little bit more about the instruments. We've introduced them a little bit, but since you have an intimate knowledge of both ground-based instruments and spaceborne instruments. Let's talk a little bit about the GPM microwave imager, the GMI, and the DPR. How exactly do they work?
Okay, so the GMI is a passive microwave imager that stares down at the Earth actually as the instrument is rotating in a conical fashion along the satellite track. And it's measuring upwelling microwaves that come from the surface of the Earth and the atmosphere and the clouds and the precipitation. And the precipitation is the signal that we're interested in.
Right.
And the imager itself is built with 13 different channels and 7 different microwave frequencies, and each of those frequencies is sensitive to a slightly different characteristic of the precipitation. For example, the lower frequencies are more sensitive to the emission that comes up from rain and liquid water in the column and even the surface temperature, whereas the higher frequencies are more associated with the ice higher in the storms.
Absolutely. So, we're talking about storms, right? We want to talk about the entire integrated picture, and satellites can see from above and they can see everything. But from the ground validation, how does that work? How do we measure precipitation from the ground when it varies so much? It varies, snow, blizzards in one place, drought in another. How do we get a sense of what's happening from the ground when there's so many different types of precipitation in different places?
Right. So for GPM ground validation, you really have to be concerned about sort of the broad amounts and types and varieties of precipitation that you're sampling. So that requires us to verify the accuracy in a lot of different environments. And really the whole objective of ground validation is to connect the dots between what we see at the surface and what's going on in the different types of clouds we see and what the satellite measures from space. And so we do that a bunch of different ways, and one way is to do field campaigns, right? So we do field campaigns in a bunch of different environments. And we use rain gauges and we use radars, we connect the dots there. The idea is to go places like, we've gone to places like Oklahoma to look at deep severe thunderstorms in the summertime, Canada to look at snow, Finland even to look at light rain and snow in a cold climate there. And we use a bunch of instruments, different types of instruments to do this. We use aircraft, for example, to give us sort of a top-down view, a satellite simulator if you like. So there we're flying instruments that look something like what we would, or collect information, something like what we would collect from a satellite. Secondly, we use other aircraft that actually penetrate the clouds and look at the precipitation particles in the clouds. And then we look at, from the ground aspect, we're using a bunch of radars, different types of radars and gauges to scan the clouds. And the idea there is to get this top-down measurement from what the satellite would see in space all the way down to the ground, and then involve the clouds in between, because that's what's producing the precipitation.
Right. So I remember a recent field campaign was in Iowa looking at hydrology and intense precipitation. And I remember there were some pretty crazy storms coming out of there. What was one of the most amazing cases that you saw from that field campaign?
Actually, Iowa was very interesting because we went out there to sample thunderstorms and summer precipitation, and we ended up starting out with snow, which was great. And then we transitioned actually to severe storms. And one day we had a case where we had 5 supercell thunderstorms tracked right across my radar scope, and it was actually kind of scary at the time, but very cool. And so we connected the ice process aloft to the rain that was being produced at the surface.
Wow, that's amazing. That's unbelievable. And so once a satellite is launched, we're talking about GPM as a core satellite, as a constellation, but does the ground validation work after launch? How do we connect the dots between what the satellites are seeing above our Earth and the surface? Is there a way to kind of evaluate or correct the measurements?
Right. So once the satellite launches here, we'll be collecting, or continue to collect, our advanced radar and rain gauge and precipitation gauge measurements all over the continental United States for sure. But this is a global problem, so we've got a bunch of global or international partners that have partners also that'll be helping us with ground validation. And then to evaluate the products, we actually can take our ground validation data sets, combine them with the products from the satellite, and then you use that as a benchmark to see how the products from the satellite can be used in societal applications, like ranging from flood prediction, for example, water resource management, weather studies of weather and climate. So those are the kinds of things we can do with ground validation data.
Wow, that's amazing.
Now, so, Walt, we have a question that's come in using the hashtag GPM. And for people watching, please send your questions this way. Just use the hashtag GPM, and we'll be able to find them and ask them live on the air. And I have one that I think, hopefully, Walt, you'll be able to answer. It's from @LostMechaSoft. And the question is, with all the radar devices that exist on and above Earth, how likely are they to interfere with each other?
Yeah, well, actually, that can be a problem for radars. Right now, it's not so much a problem for the active radars. There can be a little bit of a problem, actually, interference with the radiometers, because some of the frequencies are pretty close, and they're very sensitive. So a lot of work's gone into actually mitigating some of the interference issues that might happen with that.
And also, we just got an update. As I mentioned, if you want to be following on the absolute latest, follow at NASA Rain. It's at NASA_rain. And I'm just going to read it here. It's GPM status update, second flight attitude control test completed, and it's ready to go. So we're still hearing that the launch window is going to open at 1:37 p.m. East Coast time. Walt, I have one more other question for you. And when it comes to doing ground validation, once the satellite goes up, does your job change significantly or with the new data, or is it following into the same groundwork you've been building up?
Yeah, to some extent we continue on with the things we've been doing, but it does change a little bit because now we transition to actually trying to make sure that the products that, that we're collecting now from space actually do seem to be consistent with what we're measuring at the ground. But we'll continue to do our field campaigns. We're doing one here in May in North Carolina that's looking at precipitation over mountains. There, the idea is to keep improving the algorithms or the methods we use to retrieve the precipitation from space.
And now we did, when you were doing the one out in Iowa, we did what we call a hangout, where we had a webcam there in the box, and it was really neat because you think sometimes that scientists are working in very posh labs with big white coats, and you guys were all crammed into a trailer, right?
That's right. We're always crammed into trailers. That's the
most
whole
of your
nature of the
job is
business.
crammed
Yeah,
into trailers.
I live in trailers when I go on the road. That's it. Yeah.
NASA scientist in trailers.
Yeah,
Nice.
yeah.
Well, thank you so much for joining us,
Thank you.
Walt. That's Walt Petersen. He's the GPM Ground Validation Science Manager, and he's based out at NASA's Walt Space Flight Facility out on the East Coast. We are here live on NASA TV, getting ready to watch, hopefully, the launch of the GPM Core satellite. It is the Core satellite because it's going to be joining the constellation of international satellites that are all the entire GPM mission. And I see we've got back now the picture of the rocket that's hopefully going to take GPM into orbit. The image that you see over my shoulder here is live from there at the launch site in Japan. I don't know what the flames are, but I have heard that everything's going fine. So, and now, Dalia, I know you know many people who were there on the island. Have you been hearing updates from them on how things are going today?
We have, I mean, I know that everybody is very excited. All the ground systems thus far, everything leading up has really checked out, including your most recent update. We found out that the rollout, moving the spacecraft sitting on board a Mitsubishi H-IIA rocket was rolled out. It took about a half an hour, and the propellant, the fuel was included in, was loaded inside, and so we are. Seems like we are getting ready. This is most recent footage of the rollout of this H-IIA rocket onto the second launch pad at Tanegashima Space Center. Now, when the actual launch happens, almost everybody is going to have to stay well away from this because they actually have to pump water up to the launch pad to make sure that everything is. That everything is okay and that the sounds, the vibrations of the launch don't actually damage the rocket or the flight center.
And as we mentioned, so that's one of the reasons why the launch pad for this rocket is on an island. It's remote, there's not a lot of wildlife nearby. They really try to lessen the amount of effect the wildlife can have on these launches. One of the people who is there right now in Japan getting ready for this launch is our GPM project scientist, and I think we have a little bit of footage that she recorded before she left. So let's see if we can watch that.
The precipitation data that we get from the Global Precipitation Measurement Mission is vital for every inhabitant on Earth. Why? Because of all the water available on this Earth, less than 1% of it is fresh water. And we need to know where that fresh water exists and where we have new sources of that. The Global Precipitation Measurement Mission is going to be able to measure precipitation both globally and at the local scale. This is the first NASA mission specifically designed to measure falling snow. Falling snow is very important in terms of precipitation, especially in places like California, where their majority of their water resources comes in the form of snowpacks. And in fact, they're experiencing a drought right now, something that GPM would be able to tell us. For GPM, there's going to be science and societal benefits. One of the societal benefits requires near real-time data. These are people that want to do hurricane forecasting, flood forecasting, landslides. And so the data from GPM will be released on NASA websites within 1 to 3 hours after we collect the data. This is vital for emergency management to plan evacuations when needed. One of the fantastic things about the Global Precipitation Measurement mission is that the satellite we're launching today is actually one piece of a big puzzle. And that big puzzle is many other satellites, about 10 other satellites, that we're going to be able to provide data everywhere in the world every 3 hours. And we use both national and international partners to make sure that we are able to provide this precipitation data so vital for humanity. GPM, with its international satellite sensors and its international ground validation partners, is truly a global precipitation measurement mission with a global team.
You're watching live NASA television coverage of the upcoming launch of the GPM mission. GPM stands for the Global Precipitation Measurement Mission, and the satellite that's going up today is being called the core satellite because it's going to be part of a larger constellation that's going to get us data about rain, snow, all kinds of precipitation. That data is going to be flowing back in every 3 hours. We just saw GPM project scientist Gail Skowronek-Jackson. She's there in Japan now, getting ready to watch that footage. I'm Aries Keck, and I'm here at NASA Goddard, joined by my co-host Dalia Kirschbaum on the GPM mission. And now joining us as well is Tom Wagner. Tom is the NASA program scientist for the cryosphere. Thanks for joining us, Tom.
Hey, thanks for having me.
All right, so my very first question is, what is a cryosphere? It sounds like a big ball of ice.
Yeah, and that's literally what it is. It's all the frozen parts of the Earth, you know? And so we talk about the ice and snow, but also the big polar ice sheets of Greenland and Antarctica and the sea ice.
Very cool. So GPM is launching, we hope very soon, but it's actually the first in a series of Earth science satellites that are going to be launching this year called Earth Right Now. Can you talk a little bit more about what's in it, that constellation?
Yeah, this is a big year for NASA Earth Sciences with 5 launches. And after GPM, there's the OCO-2 satellite, which is going to tell us about the sources and sinks for carbon dioxide in our atmosphere. And then after that is SMAP, which is going to look literally at the last hiding place for water on the Earth. It's going to go and look at how much water is in the soils. And that's really important for preloading weather and also looking at drought. And then after that, there are 2 missions to the International Space Station. One called RapidScat that's going to tell us about wind speeds over the ocean. Another one called CATS that's going to tell us about particulates in the atmosphere, pollution, and other things.
So I'm an Earth scientist, and I'm super excited about GPM and all of the science satellites, but why, we get this question a lot, why is NASA studying and putting so much energy in Earth sciences?
Yeah, I know, you think of NASA and you always think of like the Mars rovers and things like that, but since NASA's inception in the 1950s, Earth science has been part of the mandate. And the simple thing is this, the Earth is big. And if you want to understand it as a system, you need something that can make measurements all over the place all the time. And that's why we have 17 orbiting missions right now studying the Earth. I mean, there's so many that some of them are even organized in a train.
Wow, so tell me a little bit more about this train. I heard it's the A train?
Yeah, it's called the A train because it crosses the equator right in the early afternoon. And what it does is, so you have satellites measuring different things, but they're kind of coordinated one right behind the other. So like one is giving you temperature, the other one is giving you cloud structure. And that's how we put all that information together to get at the processes that control the Earth.
So, the A train or GPM is measuring microwave energy, right? Coming off precipitation, and we use that energy to figure out what's happening. But how are other satellites using, parts of the electromagnetic spectrum to figure out what's happening on Earth? Are they taking pictures? What are they doing?
Yeah, they're using all different parts of the spectrum, and they're even looking at things like the gravitational pull of the Earth and how that varies. But it's amazing when you think about it. Everything from pictures all the way through to GRACE, which is like this pair of satellites that orbits very closely together, and as it floats over the Earth, by measuring the distance between the two, we can actually measure changes in mass, say, of the ice sheets over the Earth's surface, or where water is being stored on continents versus the ocean. But then there are even these amazing satellites like Calypso and CloudSat, which shoot lasers and radars into clouds to get at their structures. There's just all different kinds of things going on that we all put together to get this picture of the Earth.
That's amazing. So TRMM, for example, was initially designed at the monthly time scale to look at tropical convection. And we learned that we could get so much more from it, looking at the internal structure of storms, making measurements that we get every 3 hours. So are there other types of satellites that have been kind of repurposed or found other breakthroughs?
Yeah, I think that's one of the amazing things. It's always, you launch a satellite with an intended set of goals, but then you can clever people figure out all kinds of other ways to use them. Like even like GPS, people use it for positioning, but other people look at how the GPS signals are affected by the atmosphere to make other inferences about the Earth. Nobody thought, like with the GRACE satellites, we thought we were going to measure a static field on the Earth. Nobody realized they were going to be sensitive enough to tell us that we were losing ice from Greenland and we're losing ice rapidly, or that We can even measure whether we're losing ice in the north or the south. But you know, besides the satellites, NASA's also got this amazing array of airplanes.
Really?
Yeah.
So they fly airplanes over storms? They fly airplanes over the Arctic?
Airplanes over storms. This year we actually have airplanes going literally from the South Pole to the North Pole and all over in between the tropics, looking at clouds, looking at how the ice is changing. And the NASA planes are pretty cool. Some of them are like retired spy planes. Some of them are like a DC-8 that you might have flown on, but ours has a bunch of holes cut in it.
Very cool. So it seems, you know, we have all of these different earth science satellites measuring ice caps, polar regions, measuring precipitation and everything in the tropics. But, you know, so it tells us about the water cycle. But in terms of an integrated earth system, how do these satellites tell us about our entire integrated system and how it might be changing in a changing climate?
You know, I think probably one of the most important things we've learned through satellite measurements is that the planet is interconnected. You know, and even doing things like losing the Arctic sea ice cap on the top of the planet affects our weather all around the globe. And what you do with satellites is, you know, we develop these models of the Earth. We try to figure out how heat and mass move around, and the satellites give us the fundamental data to develop and test those.
I'm going to interrupt you right now because it seems like we have mission control here at Goddard, and we have apparently a go or no-go call. We're going to see if we can get you that footage and that audio. It'll pop up on the screen. As I mentioned earlier, as we wait to see if we can get it, both mission control and launch operations are here at Goddard. All right, and you can see them in there. Okay, apparently they're doing the go, no go, and it went really quickly, but I also want to stay on this image if we can for a minute because you can see the entire team in there watching and monitoring this launch as it gets ready to go. There's somebody looking at the camera and smiling. I think they see themselves on NASA TV. Not only is the mission control operations here at NASA Goddard, we also have launch operations here at Goddard. And that's here at Goddard because they're also sort of mirroring what's happening in Japan. There's the other there's mission operations. We were just looking at launch operations.
That's right. And once the satellite is actually launched to its altitude of 253 miles, or about 407 kilometers, Mission Operations Control is going to be running the satellite. It's going to come here to NASA Goddard, and they're going to be the ones sending up the commands to the actual spacecraft, telling it when it needs to do a maneuver, and all about uplinking and downlinking data and software.
And now speaking of maneuvers and uplinks and downlinks, as I mentioned, we're taking your questions through social media. I'm monitoring Facebook and Twitter and Instagram and all the other accounts that are out there. Please use hashtag GPM so I can find you and get your questions. And I have a question that I think Tom might be able to answer. I'm going to condense it a little bit because this person knows a lot more about coronal mass ejections than I do. But at Big John 106 asks, with a CME, which is a coronal mass ejection, which is one of those things where energy comes from the sun towards, well, out all over, but sometimes towards Earth. With a CME just detected, will solar weather prevent the launch?
Oh, that's a good question. I don't know, but I guarantee they're monitoring that very, very closely. You know, I think it depends on the size of it. But one of the amazing things is that there are enough satellites in space that we actually get warnings on space weather, and we're able to make decisions and protect things because of that.
And one of the satellites that's coming up pretty soon, I think launching next year, the MMS mission, will also help to understand our Earth's magnetosphere and look at some of that radiation that we're getting in our magnetosphere coming from the sun as well.
And now, speaking of MMS, we have not only launch parties happening all over the country. I know there's a big one out there in Texas. I know there's one here at the NASA Goddard Visitor Center. There was also a few tours of the area today, and I was helping on those tours. I got stuck behind one of the 4 MMS spacecraft as they were moving it from one test area here at NASA Goddard over to another. I was texting people being like, I'm going to be 5 minutes late because I'm trailing behind a spacecraft about the size of this desk.
That's something you get to say every day.
Yeah, right. That's all here at NASA Goddard Space Flight Center. When it comes to the launch parties, I think we have some footage of some people who managed to run up to our visitor center here at NASA Goddard and check in with all the people taking part in the launch party there. So let's see if we can watch that.
Our chair is a hard surface. Brilliant, brilliant, brilliant. I love when people think outside the box. And your middle initial, that you should know. Circle the best answer, so just one. A couple people are doing some real good design challenge here.
Space. What you're going to do in here, what we're going to talk about in here, rain gauge, something to hold the rain into. So a pretty simple concept, right? You have something that you put try to engineer something that can measure rain. And as a measuring cup, you don't have to use everything in your bin. I just gave you some things that you could cut off the top.
Cut it off like right there, so the rain would actually go in it because of the
mark for going up. No. So you notice.
So you're watching live NASA television coverage of running up to the hopeful launch of the GPM satellite. The launch window opens from its launch site in Japan at 1:37 p.m. East Coast time. That's just about 30 minutes from now. I have an analog clock there, so I can't do the math that quickly. We're going to be showing you that launch footage as it happens live. Right now, we're joined by Dr. Dalia Kirschbaum with the GPM mission and by Tom Wagner from the Cryosphere Division up at NASA headquarters. Thanks so much for joining us for this live coverage.
So as we cut in from this feed, we were kind of geeking out talking about snow, and we're so excited about snow because GPM is one of the first satellite specifically designed to measure falling snow. And given that your specialty is the cryosphere, one question is, okay, there's a lot we don't know about snow. So what do we not know about snow?
Yeah, we all make snowballs, so it's like we have a personal experience
Exactly.
with it. GPM is really important because we're going to get snow in the air. Another thing we were about, though, is snow on the ground. And snow is really important because it serves as a battery that stores water for us during the summer. And it's a more reflective surface that reflects sunlight back into space. But one of the things that NASA also does is assemble great big data records. And so you think about, we take for granted that now we have satellites that take these pictures all over the planet and we can map snow automatically. Back in the 70s, we couldn't do that. So one of the projects we just completed was to produce snow maps, like literally taking the hand-drawn snow maps from back in the day and make a consistent record that goes all the way through to now. Now, the million-dollar question is this. What's happening to the snow? Is there less of it? Is it melting earlier? And so one of the things we're finding is that right now, it doesn't look like there's necessarily less snow, that's something we're working on. But what it does look like is the snow definitely melts faster. How this plays out, let's say you're running the H-IIA Reservoir in California, which supplies San Francisco's water. Well, you have to make a decision when you can open that reservoir, because you also have to feed the local waterways for ecological reasons, you have to generate power, but you've got to keep the reservoir filled for drinking water. And so there's some NASA scientists that have helped them by taking some of these aircraft we talk about. They go out and map the snow thickness, but then you also talk about electromagnetic spectra and how we use it. Well, they measure the reflectivity of that snow, put it all together in models, and they can help water managers figure out how soon it's going to melt.
And with GPM coming on the picture, GPM is going to be able to look at an integrated picture all the way through the atmospheric column and look at snow before it hits the ground. So you get that kind of water amount from the snow, and you can it just gives you another piece of that puzzle to tell you what's happening.
Right, and that also kind of gets into this. We really want to understand how the Earth works as a system, so we can do things, as you pointed out, like better weather forecasts now. But we're also trying to think 100 years out. We want to do better climate models to think about things like what water resources are going to be available, how much is sea level rise, how hot's it going to be, and all these pieces come together to answer that.
That's great.
Thank you so much, Tom. I want to mention, I've been mentioning #GPM. Please keep sending your questions this way. We've got a number of questions that I have to ask you, Tom, and also you, Dalia. Definitely use the #GPM. I have to note at this point, if you're writing us in Japanese, I don't speak or read Japanese, so if you can hit translate and send me what you're asking me in translate, that would be great. We do have a number of questions in English too, but just noting that our Japanese feed has blown up, and which is fantastic because it's the middle of the morning in Japan right now. Essentially, they're already on to the next day. The launch window is scheduled to open, still on schedule for it to start opening at 1:37 p.m. our time. As you can see, we're starting to get some detailed live footage from our partners in Japan that's running over my other shoulder here. And then also we're going to be sharing some tape. Actually, I've been told that's tape from before when they're getting the satellite ready to roll. Tom Wagner from NASA's Cryosphere Division. Well, a question came in earlier about, and this is a question I'm sure pains you guys and you get a lot, but why not just go outside and put a ruler down and measure snow? Why do we actually have to measure it as it falls through the sky?
Two great answers to that question. One, we want to know what's going on in the sky because also once the snow hits the ground and blows around, it's an imperfect record. And we really try to do things like we want to know what the characteristics are in the atmosphere and what kind of snow it produces, and that improves our models. Second thing, though, is this. You can go out with a ruler and you can get snow dips. Here's your problem, though. Depending on the temperature history, how warm it was that day, that snow can pack down. And so height alone doesn't produce that record we need. We need to know the snow water equivalent, or the density of the snow. And we spend great pains going out to try to measure that. It's also really important though, because that turns out to be one of the most important things for figuring out what kind of changes are happening in Greenland and Antarctica.
And now we have another question I'm sure is you get all the time, which is we're talking a lot about science measurements, but at @eWilmot has just asked on Twitter, how are these measurements going to help snowfall forecasting? Is this going to give us a better forecast for our nightly news about how much snow is going to fall, or if it's going to fall at all?
Good question, and there's a couple things to consider, right? We're talking about taking the measurements that we have now to a whole new level, okay? That will ultimately get into tools that will likely improve those things.
And now, one other question that just came in through Twitter was, we've talked a lot about snow. Does it do all kinds of rain, heavy rain, light rain, fog?
Does GPM answer that question?
Excuse me. We're gonna see if we can reach the other control room with a go, no go call.
No LCC violations.
CSO?
CSOs go with no LCC violations.
Copy that.
Okay, I guess that's it. If you were listening carefully, you're probably able to hear just a little bit of that as they were going through go, no go. One last question for you, Tom.
Yeah.
I keep getting ready for these go, no go. What exactly do we mean by a go, no go? What's happening in those control rooms?
Well, I think they're literally going person to person, and everybody in there has responsibility for a specific thing, and they go, are we a green light on this parameter, on this parameter? And they go down, go, 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 go all through them. It's pretty exciting.
And I think as we look at these mission operations control and launch control, you see how many people are involved, and that's just at NASA Goddard. You know, Candace Carlisle was saying how there's 300 people that built the satellite at Goddard, but you can imagine how many people both here and at Tanegashima are actively watching and waiting and working really hard to make sure that everything goes smoothly. So, you know, just a shout out to everybody that is working on the satellite, working on the launch. We're just really excited from our little launch party here at in the studio.
And speaking of shout outs, it's scrolled down in all the tweets that are coming in, but I did see one thing of different university scientists being like, shout out to so-and-so, shout out to so-and-so, using the GPM hashtag. So if you're following along, follow that, and you'll see all the different scientists. And then there's also all the scientists like yourself, Dalia, who are waiting for the data to come in for their research.
That's right.
I've been mentioning you're a mission scientist, but we haven't talked about your expertise at all. Can you tell us a little bit what you're going to do when the satellite gets up in orbit and starts giving us data?
You know, I'm so excited for this satellite for a number of reasons, but one is that we will have this amazing global data set, which will tell us about, you know, where farmers should plant their crops or give them advice or give them data, you know, where we might be having diseases, or even looking at natural disasters, floods and landslides and tropical cyclones. You know, those huge disasters really tell us a lot about, you know, how people are impacted by weather and how they might be changing over time.
And now we just have a question in from Twitter, Salsa with Sylvia, and she wants to know, why is GPM launching from Japan? Why are we not doing it here in the United States?
A great question. You know, and GPM is an international mission co-led by NASA and JAXA, the Japan Aerospace Exploration Agency, and as part of that agreement, NASA developed a spacecraft about the size of a small fire truck, but twice as heavy, the largest satellite built and assembled at Goddard to date, and they also provided one of the instruments, the radiometer, in contract with Ball Aerospace. Now, JAXA actually provided the 2 radars that we have on board, and they're launching the satellite on a Mitsubishi, a commercial H-IIA rocket. And so this is just an amazing partnership to show how we can leverage assets between countries and really do much more with an international team for an international problem.
It also gets at, too, we spend a lot of time taking data from other satellites, you know, international satellites, and pulling them all together to do the science that we need to do.
Absolutely.
And now we're getting the live feed from our partners in Japan of the rocket. This is an H-IIA rocket. If you're familiar with rockets, it's roughly equivalent to an Atlas rocket. And look at that big GPM graphic on the side of it.
So it's an interesting thing about the rocket is actually the GPM satellite is sitting kind of tucked up right in the top in the fairings. But in order to put it in there, they actually had to build a whole structure and lift up and put the fairings on top. It's a very involved process, and everything went extremely well. But this has been a very successful rocket, and so we're really excited that Japan is launching it.
And that brings me to not really a question, but when we're looking at the rocket, it looks, you know, it's a certain shape. But when we show these pictures of the satellite, it's all unfurled. is it all just tucked up in the very top, sort of like a cocoon?
Yeah, it kind of all comes in this capsule, and I have to preface this by saying I'm not an engineer. One of the things I think is particularly cool about the solar rays as you see them unfold is they actually are on springs. And so rather than having an arm that kind of electronically extends, it uses all of the forces, gravity or non-gravity when you're in space, and it just releases the springs and they automatically unfold. And so that's kind of a cool thing about how the solar rays, which will be deployed shortly after the launch, come into their existence.
That actually, direct question from @Andrew6732. And by the way, if you want to send some questions, use hashtag GPM. Andrew Little, I don't know if we know, us here know the answer to that, but how long does the satellite take to open fully?
Well, I think we have that information, and I'm going to use this as a teaser so that you can watch the launch and you can see how long it takes, because we will have all that information coming up. But you know, I kind of wanted to go back, if it's okay, to looking at tropical cyclones and looking at storms and blizzards, because you know, since we have a little bit more time to discuss the science and before you know all the engineering starts and the satellite hopefully makes its way into orbit, one of the things I think that TRMM, the Tropical Rainfall Measuring Mission, really contributed is to our understanding of how hurricanes or hurricanes, typhoons, or the general term tropical cyclones, really intensify and move. And so GPM, since we're able to kind of continue that orbit, we're able to go from the Arctic to the Antarctic Circle, we're actually able to look at those storms in 3D as they move up the coast. So if you take Hurricane Sandy, for example, you know, Hurricane Sandy, TRMM had this amazing image. You can see the bands between 35 degrees north-south, but just after it got off above that latitude, they weren't able to see anything. And so GPM, because of its advanced instrumentation and also its ability to go from the Arctic to the Antarctic Circle, we're able to get a better sense of what's happening with these big storms and provide that first view of extratropical systems out over the oceans in 3D. You
know, there's some neat visualizations of that too at the Goddard Visualization Center. And one of the things we're doing this year is actually flying the NASA Global Hawk over storms to do additional mapping. And there's some great visualizations that show that combine TRMM data with what you can get from an aircraft.
We have all those visualizations, some of those we showed before, and many, many others. Just go to www.nasa.gov. Right now, I believe GPM has taken over that entire website, so we don't have to send you to another one. But if you go there, you'll see all the different visualizations and things like that. There you'll also see messages from the head of NASA, Charles Bolden. And right now, we're going to show you a thing that he sent us in celebration of the GPM mission. So right now, let's go to the head of NASA himself, Charles Bolden.
This year, for the first time in more than a decade, 5 NASA Earth science missions will be launched into space in 1 year. Together with NASA's existing fleet of satellites, airborne missions, and researchers, these new missions will help address some of the critical challenges facing our planet today and in the future, such as climate change, sea level rise, access to freshwater resources, and extreme weather events. Today, the Global Precipitation Measurement Core Observatory heads to space. This is a joint Earth-observing mission between NASA and the Japan Aerospace Exploration Agency, or JAXA. This is the start of a constellation of satellites with our international partners that will produce the first global observations of rainfall and snowfall. GPM's revolutionary new data will help answer questions about our planet's life-sustaining water cycle and improve weather forecasting and water resource management. All of our new Earth science missions highlight NASA's role as an innovative leader in Earth and climate science, and we're constantly expanding our view of the planet from space. Our amazing team of experts is building on decades of work to help us create and maintain a long-term benchmark of information about our planet and its environmental systems. We're following up the GPM launch with 4 more Earth science launches this year. This is an unprecedented achievement and a tangible example of our commitment to understanding our home planet and its changes to become better stewards. Please join me in congratulating the NASA and JAXA teams that made this extraordinary launch possible. I hope you'll join me in following GPM and its achievements.
Thank you so much for joining us. We're hopefully about 15 minutes away from the launch window opening, and we're going to be bringing you that launch here live. You're watching NASA TV. I'm Aries Keck here at NASA Goddard Space Flight Center, and I'm joined for this broadcast by Dr. Dalia Kirschbaum of the GPM mission. She's a GPM project scientist.
Mission scientist.
I'm sorry, GPM mission scientist. And I want to thank our guests who have joined us, Walt Petersen, who is with the ground validation group out at Wallops, and Tom Wagner, who's the NASA program scientist for the cryosphere. Dalia, real quick, the science that you particularly study is landslides. Can you tell us a little bit about what that works and how the GPM data is going to fit to something so much on the ground?
Absolutely. You know, landslides are a really local feature for the most part. They only happen in small areas. And so what I've been doing with my research and with others is to kind of see how we can figure out what's happening from a bigger perspective. So if you think about what you need for a landslide, you need to know how much it's raining, you need to know if there's a steep slope, what the soil and the geology look like. And so it turns out that we can actually use satellite data like TRMM and like GPM to figure out what's happening, where and when landslides are happening around the world. And so that's a study of an area of ongoing research, but something that, that I'm very excited that GPM will help to improve our estimates.
Most definitely. It's amazing how much precipitation does with so much around the world. One thing I want to touch on real quickly as we get ready to show this footage from the live footage from Japan is the true human impact with diseases that can be brought about by waterborne mosquitoes and things like that. Is GPM actually going to tell us about the spread of disease?
Absolutely. We have scientists, and there are scientists all over the world using TRMM data currently to uncover ideas about, you know, what happens with malaria or what happens with encephalitis, both mosquito-borne illnesses. There's other examples of how we can use rainfall data to look at things like schistosomiasis, which is a snail-borne disease out in Ethiopia, of one of the places, and even looking at black plague in Uganda. And so it takes a tremendous science team to kind of be able to look at this data. And so in addition to having our science team members, about 50 of them around the world, there's the international precipitation community and science community that will use this global data to uncover everything from farming in Africa to monsoons in Asia and drought in California.
Fantastic. Now I'm hearing that we're still scheduled for a launch window to open at 1:37 p.m. East Coast time. That's roughly about a little over 10 minutes from now. So we're going to be bringing you the footage that we have from our partners in JAXA. I mean, in Japan, it's partners both with the Japanese Aerospace Agency and with NASA, who are out there in Japan. We had a question coming in about how heavy is the actual GPM core satellite and how long it's going to live. And Di, I know you wanted to talk a little about the effort it took to get that core satellite from here at Goddard all the way to its Japanese launch site.
Sure. Where the actual satellite, fully fueled, is over 8,000 pounds, excuse me. And I said again, it's kind of the size of a small fire truck, or if you think about the corporate jet, tip to tip. But it's really big. And so to try to get it from NASA Goddard, where the satellite was built, it was loaded onto a shipping container and then brought to Andrews Air Force Base, where it was loaded on a C-5 Galaxy airplane, one of the biggest they have. Now the plan was to refuel in the air, but it ended up making a stop in Anchorage, Alaska, but then flew to Kitakyushu, Japan, where it was loaded onto a barge, and it made its way all the way to the southern tip of Tanegashima Space Center in Japan, where it was then. So this is it loading onto the barge, and this is the final process of driving it to the actual space center. So while it was a long process and it was hampered by weather, you know, ironically in a few ways, it was safely delivered to Tanegashima, where it was prepared for launch. It was loaded onto the H-IIA rocket, and now it is awaiting its final journey into space, where it'll be about an altitude of 253 miles or 407 kilometers, and it will hopefully provide us with amazing data for years to come. And you mentioned how long it's going to last, so the mission design is actually for 3 to 5 years, but we hope that there'll be fuel to last much longer than that.
So it's a series of trucks, planes, boats, now hopefully finally a rocket. We're going to hopefully get you that footage of the rocket going up as it comes into us live. The launch window is still supposed to scheduled at 1:37 p.m. That's East Coast time. Apparently, of course, it's very early in the morning there in Japan. What you're looking at right now is footage that was sent to us earlier in the day from Japan of the tower rollout, and you can see quite clearly there. It's a really a picturesque spot to send off a rocket there on the island. Dalia, we're getting a number of questions that come in through social media, so please send us questions. It's #GPM. And one of the questions has to do about, we mentioned the equivalent size, that this rocket is the equivalent size of an Atlas rocket. Can you tell us a little bit more about the rocket itself, like who built it and that part of it?
So it's actually a Mitsubishi rocket, so it's commercially. It's a commercial rocket, and the H-IIA has had a large number of successes. One of the things that I think is actually kind of cool is about the fuel, which we'll hopefully see quite soon. And so it actually is composed of 2 solid booster rockets. And we actually just heard word that the spacecraft is now on internal power. Yep. So what you're seeing right there, they currently lit the liquid fuel, I believe, and so they are preparing the spacecraft. What happens upon launch is actually the solid boosters get ignited and they're fully engaged right away. So you have this huge spark, and then they get burned out, and then the liquid fuel from the stage 1 and then the stage 2 go.
And now you mentioned earlier how many kilometers, once the satellite's finally in orbit, it is, but is there an equivalent distance of how far up in orbit GPM is going to be versus on the ground here in the world?
Yeah, so if you think about it, if we're standing under the GPM rocket, it's going to be about the distance between New York City and Washington, D.C. So it gives you the sense. It's in a low Earth orbit, and so it needs fuel to maintain its orbit. And again, it's inclined at about 65 degrees, which will take it from the Arctic to the Antarctic Circle. And the reason that it does that is because it's able to sample precipitation at different times of the day over different areas. So if you think about an island, which we would love to be on right now, I'm sure. If you think about that, the precipitation, the rain in the morning is different. You get a big thunderstorm, then it's lovely, and then it's different at night. And so GPM wants to be able to sample that at different times of the day to see the whole cycle of precipitation on Earth.
And now that we've watched some of the footage of what's called tower rollback as this rocket was actually being set up on its launch pad. Shortly we're going to get you some live pictures of the rocket as it's there. It's the middle of the morning, early morning there in Japan. And there you see it. So we're going to mention that all that beautiful scenery we can see in the earlier footage is in complete darkness, but they've lit up the rocket quite beautifully there on the launch pad. And now the launch window is still scheduled to open at 1:37 p.m. East Coast time. And by opening, that means that is the first attempt in this launch window that we have today. It's an hour-long opportunity to send this rocket up. That's the first attempt that they will go. If it doesn't go then, they will reset and then try to go again. And we'll be bringing you updates live as they happen. So we have just about, glancing at the clock, just about 6 minutes left to go until hopefully we see everything go up. As far as I've heard, everything is working along fine. We are going to be bringing you some of the audio from our colleagues in Japan of the rocket liftoff. It may be in Japanese, so we're going to do our best here to relay what we know is supposed to happen as it goes along. And also, please keep sending us your questions on social media. Use the #GPM. We really appreciate it. A bunch of people were asking the exact question we just answered, which is when GPM is actually in orbit, how far up is it going to be? Does it have to be in a low orbit, Earth orbit, to do the science it does, or is there any other reason? Would it just to keep it out of the way of other things, or is it because it has to be that low?
Well, it's at the orbit that it's at because the instruments on board are designed to measure down to the particle scale, looking at individual precipitation. And so by having a low Earth orbit, we're able to have those really advanced microwave instruments to look at precipitation. And so what you're seeing right now, again, is live from Tanegashima Space Center in Japan.
And I'm hearing that we have some English translation of the coverage there. We're going to go to it live.